All around us, there's this kind of invisible intelligence at work. It's managing our environment, it's powering our industries, and it's guiding our technology with a precision that we pretty much just take for granted. These are control systems, and they're the unseen engines that are quietly shaping our modern world. So what's the connection? What do a car's cruise control, the thermostat in your house, and a massive, complex, smart factory actually have in common? Well, it turns out they all run on the exact same fundamental principle: automatic control. So in this explainer, we're going to take a journey. We'll start with the basics of how our world went on autopilot. Then we'll get into the real heart of it, the feedback loop. We'll learn the language of control, see how it evolved into something truly intelligent, and finally see how it all comes together to form the brain of a modern smart factory. Okay, let's get into it. To really understand where we are now, we first have to look at where we came from. We'll start with that big shift, from a world that we controlled by hand to one that pretty much runs on its own. Think about it. It really wasn't that long ago that every little thing required our direct human touch. If you wanted something to change, say more heat from the stove, a different direction for the car, more water through a pipe, you had to be right there, constantly watching and making those little adjustments yourself. But here's the thing about manual control. It has its limits. We're human, we get tired, we make mistakes, and we just can't react in a split second. Automatic systems, on the other hand, completely change the game. They're relentless, they're incredibly precise, and they can operate all on their own, which frees us from having to constantly supervise everything. So, how does a system actually control itself? Well, the magic ingredient is a concept that's both really simple and incredibly powerful. It's called the feedback loop. Now, what's so fascinating about a diagram like this is that it's not a one-way street. It's circular. It's designed to correct itself. The system is basically asking itself over and over again, am I doing what I'm supposed to be doing? It measures its own performance, compares that to the goal, and then immediately uses that difference, the error, to figure out its very next move. This ability to self-correct is the absolute foundation of all automatic control. And this is really the crucial point. Feedback is just information. It's the system telling itself, hey, this is where I am right now. It's this self-awareness that allows it to adapt and fix its own mistakes without any human having to step in. Your thermostat at home is the perfect everyday example of this. It doesn't just blindly turn the heat on and hope for the best. Nope. It has one job: to constantly check, is the room warm enough yet? It measures, it compares, and it acts, all based on that continuous loop of information, of feedback. All right, so to really get how that feedback loop works, we need to break it down a bit. We're going to zoom in on that diagram we just saw and learn the language of control so we can understand what each part is actually doing. So, every single control loop is made of these parts working together. It all starts with the input, or set point. That's your goal. Then you have the controller, which is the brain of the operation. Its job is to manage the plant. That's the actual thing you're trying to control, like a heater or a motor. A sensor then measures the output, which is the actual result. And finally, that measurement gets sent back as feedback so the controller can decide what to do next. It's a constant conversation. Let's put some numbers on our thermostat example. Okay, so you set your goal, the set point, to 22 degrees Celsius. The sensor, the thermometer, measures the room and says, hey, it's only 20 degrees in here. The controller sees that difference, a 2-degree error, and immediately sends a command to the heater, which is our plant, telling it to turn on. That loop keeps running, measuring, comparing, acting, until the sensor finally reports back that the error is 0. It's really that simple, and that elegant. And this comparison perfectly highlights the two big philosophies in control systems. On one side, you have an open-loop system, like a basic toaster. You set the timer and it just goes. It has no idea if your toast is perfectly golden or a burnt crisp. On the other side, a closed-loop system, like your car's cruise control, is constantly measuring your speed and adjusting the engine to handle things like hills or wind. It's always adapting to keep you on target. Now, that brain we talked about, the controller, it hasn't just been sitting still all these years. It's actually gone through this amazing evolution, getting smarter and way more capable with every new leap in technology. We started out in the 1920s with these really clever mechanical gadgets. Then the digital revolution hit in the 70s, and we moved control from gears and levers into software. By the 90s, we were developing what we call intelligent controllers, which has led us all the way to today's AI-driven systems that can actually learn and make their own decisions. For decades, this thing called the PID controller has been the undisputed champion of industry. Now, without getting lost in the math, its genius is that it looks at three things: The P part reacts to the error that's happening right now. The I part looks back and corrects for any small errors that have built up over time. And the D part is really clever. It actually tries to predict where the error is going in the future. Present, past, and future, all working together. The next big leap was a move toward intelligent control, with things like fuzzy logic. See, instead of thinking in black and white terms, like just on or off, fuzzy logic thinks in shades of gray. It can understand concepts like a little too cold or getting warmer. This lets it handle ambiguity and make decisions that feel a lot more like human intuition. So, where does all of this technology ultimately lead? Well, it all comes together in the modern idea of the smart factory, where all these individual control systems connect to form a vast, intelligent network, kind of like a nervous system for the whole building. A smart factory is really built in layers. Down at the very bottom, you have the shop floor, all the machines and sensors creating a flood of raw data. A layer up, you have SCADA systems that give you a real-time dashboard to see what's happening. Above that is the MES, the factory's brain, which understands why things are happening and directs the work. And at the very top, the ERP sets the big business goals. So instructions flow down from the top and data flows up from the bottom. And if we zoom right back in on one of those machines on the floor, what do we find? Our old friend, the feedback loop, working away. But here we see a key new part, the actuator. If the controller is the brain making the decision, the actuator is the muscle that carries it out. It's the motor, the valve, or the robotic arm that takes that digital command and turns it into real physical action in the world. This entire structure creates the ultimate feedback loop. Think about it. Every single action on the shop floor generates data. That data gets turned into insight by the intelligent systems above it. And that insight is then fed right back down to drive the next action, making it just a little bit smarter and a little bit better than the one before. And this really is the key takeaway here. A smart factory isn't just some piece of software you can buy. It's a system you build. It's not about having pretty dashboards on a screen. It's about creating a powerful engine for turning data into real, tangible action in the physical world. So when you step back, you can see it. From the simplest little device keeping your house comfortable to the most complex factories building the things we use every day, control systems are that silent, intelligent engine making it all possible. And this all leaves us with a really fascinating question to think about for the future. As these systems keep evolving from simple automation to true autonomy, where they can actually learn and decide for themselves, we have to ask, are we just building better tools that follow our instructions? Or are we starting to build the future partners that will help us create tomorrow?